All right, folks. So we've just spent a whole chapter talking about the behavior of gases, okay? So in a gas, the molecules are so far apart that in general they don't interact with each other, which is why most of the time we're able to use the ideal gas law. But when we start talking about liquids and solids, those phases of matter are more dense than gases. So if the atoms or the molecules are close enough together, they're going to interact with each other. So the kinds of interactions between individual molecules, okay, between molecules are intermolecular forces, okay? So when we see phase transitions occur between solid, liquid to gas, those all depend on what the type and strength of intermolecular forces there are within a substance that's holding those particles together. So the stronger those intermolecular forces, the more energy you're going to have to put in to overcome them. So that heat energy will be transferred to kinetic energy. So your particles will be moving more quickly, and then they'll be able to overcome those intermolecular forces. So the main type of intermolecular attractions that we need to know about are dispersion forces, also known as instantaneous dipoles, ion-dipole interactions, dipole-dipole interactions, dipole-induced dipole interactions, and hydrogen bonding. So let's have a talk about what each of those are. So first of all, dispersion forces. All substances have dispersion forces acting between their molecules. These particular types of attractive interactions come from instantaneous uneven distribution of the electrons, an instantaneous dipole. So if you think about the electron orbitals containing electrons around your molecules, at any given split second, those electrons can be unevenly distributed. So this effect is greater the more electrons there are in the molecule. So higher Z, more electrons means more polarization. It's also affected by how spread out the molecule is. So if it's like a long, thin molecule, then that electron density is more polarizable. It's easier to have a change instantaneously in how the electrons are distributed around the molecule at any given split second in time. So that means that there's higher dispersion forces acting between the molecules. So ion-dipole interactions are electrostatic. So we already know like ions, cations, anions is where you've had complete transfer of an electron. So they're a charged particle, they're charged all the time. Whereas if you have a dipole, what you have there is an uneven distribution of charge across a bond, but the molecule itself is not charged, right? So the molecule is polar due to a separation of charge, but the whole thing is still neutral overall. So you'll see an interaction between an ion and a molecule with a permanent dipole moment. So like a cation will be attracted to the negative side of a dipole within a polar molecule. An anion will be attracted to the positive side of a dipole within a polar molecule. And this is the mechanism by which a polar solvent such as water, which has a positive and a negative end, is able to pull ions from an ionic solid like salt into solution. It's the ion-dipole attraction that is facilitating that dissolution. So within a polar molecule, obviously, if you have a load of polar molecules together, there's going to be intermolecular forces acting between those polar molecules, between the permanent dipoles that they have. This is what's called a dipole-dipole interaction. So it's the type of intermolecular force between polar molecules. So obviously the strength of that dipole-dipole attraction is going to depend on how big the separation of charge is. And we already know how to work that out, right? The bigger the electronegativity difference there is in the dipole, the larger the dipole is. So the very, very strongest dipole-dipole interactions are going to be between very electronegative elements and hydrogen. So that is a nitrogen-hydrogen bond, an oxygen-hydrogen bond, and a fluorine-hydrogen bond. Those have very big electronegativity differences in those bonds, so they are highly polarizable. And this is what is called hydrogen bonding, intermolecular attractions between molecules that contain NH, OH, and FH bonds. So what about the influence of a polar molecule and a non-polar molecule? When a polar molecule comes close to a non-polar molecule, that charge that the polar molecule has, the separation of charge, will distort and affect the electron distribution around the non-polar molecule. This is called polarization, okay? So the extent to which the electron cloud can be distorted by the influence of an external charge. And this forms a temporary dipole called an induced dipole, because it's been induced by the action of the proximity of the polar molecule. So obviously the more polar the polar molecule is, or the more polarizable, the more squishy the non-polar molecule, the stronger that dipole-induced dipole interaction is going to be. Okay, so talking about applications of intermolecular forces, solubility is a big one, okay? So an ionic solid is gonna want to dissolve in a polar liquid. When you're talking about whether pure liquids are going to dissolve in each other, liquids dissolving in other liquids is what we call miscible, and they have to have the same type of intermolecular attractions in order to mix, okay? So if you have an ionic solid or a polar solute, it's going to dissolve in a polar solvent, such as water, whereas if you have a covalently bonded solid or a non-polar solute, will only dissolve in non-polar solvents. So this leads to the rule of like dissolves like. You have to have the same types of intermolecular forces between the molecules of your solute and the molecules of your solvent in order for two things to be miscible. So when you have unlike intermolecular forces, such as trying to dissolve an ionic solid in a non-polar solvent, you're not going to get a homogeneous mixture, and we call this when something's immiscible. So think of oil and water, what we formerly described as a heterogeneous mixture. Now we know enough about intermolecular forces, we can say that they are immiscible because of the dissimilar intermolecular forces they contain. So water, for example, is highly polar, right? Because it's got an OH bond, so it can actually form hydrogen bonds, and it has two lone pairs sitting around. So it's got a really big dipole moment, which is why there's so much interesting chemistry and properties of water. So polar molecules, or if you have a large molecule, a polar region within that larger molecule is going to be attracted to water because it's polar. And we have a word for this, comes from Greek, it's hydrophilic, that means water loving. If we have non-polar molecules or non-polar regions within a larger molecule, those will repel water because of the dissimilar intermolecular forces, and that's what we call hydrophobic. So, you know, phobia, spiders, scary, so they dislike water. So other applications of intermolecular forces, we know already the type and strength of intermolecular forces will affect the boiling point of a liquid. How do we describe when a liquid will boil? We use the term vapor pressure to describe at equilibrium the pressure of the gas above the surface of the liquid in a closed container due to evaporation. So when a liquid boils at its normal boiling point, what happens is that is the temperature when the vapor pressure is equal to atmospheric pressure. So we will describe a liquid as volatile if it has vapor pressure, high vapor pressure, so that it will reach atmospheric pressure at a lower temperature. Therefore, it boils at a low temperature. That's what we mean by something volatile, which is why when you go to the gas station, you fill up your car with gas, sometimes you can really smell that gasoline, right? Because it's got high vapor pressure, so it's got a fairly low boiling point, and it's what we'd call a volatile liquid. So how we relate pressure and temperature and whether something is a solid, liquid, or gas under those conditions is we use a phase diagram. So that plots pressure on the y-axis against temperature on the x-axis and has zones for where under those conditions a particular substance would be solid, liquid, or gas. So you can just find your pressure, find your temperature, and work out what phase your material is going to be in under those conditions. So we also talked to some extent, or read about water. So obviously the chemistry of water is so important in biology for life on Earth. So many chemical reactions, as we know, take place in aqueous solution. We even have an abbreviation for it, right? AQ in brackets for when things are dissolved in water. So a lot of these important properties of water come from the fact that there's hydrogen bonding between water molecules because of that high electronegativity difference between oxygen and hydrogen. So that means water has a relatively high melting and boiling point because it's got strong intermolecular forces, hydrogen bonding. It's got high surface tension and viscosity. And one very interesting and useful property if you're a fish especially is that solid ice is less dense than liquid water, okay? Always, right? We've learned like the solid phase is more dense than the liquid phase. It's the most dense phase of matter. But in ice, because of the hydrogen bonds, holds the structure open. So there's lots of space between the water molecules, that the density of ice is actually less than water. So that was enough information about liquids. We also talked about solids in this chapter, which is like my favorite chemistry. I'm a solid state chemist, right? So I'm a little bit biased. So we talked very briefly about amorphous solids where we don't have like a regular structure, but they are not as interesting as crystalline solids. I might be biased here. So crystalline solids can be metallic, ionic, or covalent, depends on what atoms are making them up and therefore what kind of bonding they contain. But what all crystalline solids have in common is a three-dimensional extended structure, which is built up from regular repeats of the smallest portion of the whole, which is called a unit cell. So the unit cell, if you translate it in three directions, X, Y, Z, will generate the entire three-dimensional crystal structure. So there's two major packing motifs, hexagonal close packing and cubic close packing, which are very efficient ways of packing spheres. So think of like oranges in a supermarket, right? You start with a two-dimensional layer of oranges, and then there's these little gaps in the top in between the oranges. The oranges are equal size, right? And those little gaps are where you put in the second layer. So the only difference between hexagonal and cubic close packing is the third layer. So for hexagonal close packing, you just go back to the original pattern. But in cubic close packing, there's you can put the oranges over the next set of holes along, so you get a three ABC layer rather than an AB layer. So we're going to just talk about cubic unit cells, which is where the edge length of the unit cell is the same along the X, Y, and Z directions. So we label the edge lengths for a cubic unit cell A, which is the lattice parameter, the length of the cubic unit cell. And for a cubic system, there's three common unit cells. There's the primitive, or you may see it called simple cubic, which is just where you have atoms just on the corner of the cube. There's the body-centered cubic, where you have the atoms on the corner of the cube plus one in the center of the cube. And then face-centered cubic, which is where you have all the corner atoms plus in the center of each face of the cube, you have another atom. And this is exactly the same structure as cubic close packing, just viewed in a different orientation. So how can we compare these unit cells in terms of packing efficiency is one way that we look at them. The more efficient packing patterns tend to be more common, that we find them in nature, etc. So more elements will tend to have like face-centered cubic and body-centered cubic arrangements than like simple cubic, right? Because of the higher packing efficiency. So when I talk about packing efficiency, I mean the percent of the volume of the cubic unit cell that's actually occupied by atoms. So if we're modeling atoms as spheres, okay, it's the volume of the spheres divided by the volume of the cube, convert to a percentage. So out of all the systems we talked about, face-centered cubing / cubic close packing and hexagonal close packing have the highest packing efficiencies. So remember, if you're trying to work out the volume of the atoms within the unit cell, remember, if an atom's on the corner of the unit cell, it's actually shared between neighboring unit cells. Same as if an atom's on the edge or the face of the unit cell, those are not 100% within that unit cell. So we can do a bit of simple geometry to relate that lattice parameter A to the radius of the atoms making up the unit cell. We just use a bit of Pythagoras, okay? So if we know the unit cell type, we can relate that to the density of the element by looking at the mass and the volume of a single unit cell. So remember, density is just the ratio between mass and volume. It's an intensive property. It doesn't matter how much stuff you have. The density of a unit cell of gold is the same density as a massive bar of gold bullion, right? It's still gold. So the last thing we talked about is forming alloys. Okay, so an alloy is a mixture of two or more metals. We particularly were talking about homogeneous alloys, which is a blend of metals. If the metals have the same crystal structure and if they have atomic radii that are close to each other, and we say within 15% for this class, we can assume they will form what's called a solid solution. Okay, we call that a substitutional alloy. So we have the minority component, the solute metal, replacing atoms of the solvent metal within the crystal lattice. So to do that, they have to have the same crystal structure and their radii have to be reasonably close together. So if there is a size mismatch, if one of the metals is significantly smaller than the other one, then the small metal is going to go into a hole in the crystal structure. So think about stacking oranges again. There's always these tiny little gaps between spheres, right? You can't ever have 100% packing efficiencies of spheres. And we give these holes a fancy name. We call them interstices. So if we have this kind of alloy where the smaller metals in interstices in the host crystal lattice, we call this an interstitial alloy. Okay, guys, so I hope you're keeping up all right with all these online materials. This is our penultimate chapter. We just have one more chapter to do to finish Gen Chem 1, which is talking about colloids, and then that will be it. So I'll see you in one more video. Okay, take care.